Okay, so the next talk is going to be about MVAPICH2 at Azure, enabling high performance on cloud. And it's going to be delivered by Dr. Jithin Jose, who's a principal software engineer at Microsoft. His work is focused on co-design of software and hardware, building blocks for high-performance computing platform, and performance optimizations. His research interests include high-performance interconnects and protocols, parallel programming models, big data and cloud computing. Before joining Microsoft, he worked at Intel and IBM Research. He has published more than 25 papers in major conferences and journals related to those research areas. Dr. Jose received his PhD degree from the ISA University in 2014. So without further ado, please proceed.
Thank you, Mustafa.
The floor is yours now.
Yep, thank you. Let me share the screen. Just a second. Are you able to see the screen?
Yes, we can, but not in presentation mode yet.
Yep, let me change that. Is it coming out good or?
It still shows the, like that. Yeah, now the full screen mode is there.
Oh, thank you.
Good.
Yeah, so in this talk, I would like to highlight the importance of software libraries or communication libraries like MVAPICH2 to really enable the high performance, right? I mean, we have the hardware generations like going very fast, but I mean, it is really important to get the best performance out of the platform, right? So I would like to highlight on that. I would like to show some of the performance numbers, etc., and then really show the improvement, right? So yeah, and as a quick outline, I'd like to introduce the latest HBV4 and NDV5. These are the two new HPC/AI SKUs. I'd like to introduce them and then go over some of the performance highlights with MVAPICH2 and some larger scale performance results. Right, so that's short outline of today's talk. And generally, if you look at Azure HPCAI VMs, right, broadly those are classified into two, the H series and the N series, right? The H series is mainly targeted at traditional MPI workloads where you have high compute and then high memory and then InfiniBand as a backend network, right? And we have different SKU versions, like starting from HP, which is the EDR, and to all the way to HBV4, which is the NDR clusters, right? And similarly on the N series, these are mainly the SKUs with GPUs. So and mainly targeted at deep learning or visualization training inference workloads, right? And we have, they can be classified into NV and NCND. And the NCND, that's the one we are going to focus on this talk. Mainly, I would like to target the SKUs which are IB enabled, which is the N series and the NCND, right? And I would like to call out that in all the IB enabled VMs, right? I mean, there's always one VM per host. So you get the full host for the VM for the end customer. And the different devices, right? The GPUs or the IB NICs, right? Those are exposed as DDAs or through SRIOV, right? So, no virtualization overhead. And the fabric is fully connected, like without oversubscription. But you handle or you isolate the different tenants, in this case, different customers, using software that's partition key-based isolation. And this is the HBV4, which is the latest in the H series. And this is powered by AMD Genoa X CPUs, and then with IB, NDR 400 gigabits per second IB. And I just quickly wanted to show how we carve out the VMs, right? So you always, this is on the cloud and these are virtualized, right? So you want, there will always be some overhead from the host from the host operating system, right? So how we avoid that for the NVM is by carving out some specific cores to the host operating system, right? So those are so those cores will not be appearing on the end VM or the customer VM, and only the host or Hyper-V cores, Hyper-V processors will be landing only on those specific cores. So that's why even the entire CPU, it has like say 128 cores, right? Or in this case 192, right? We take out some of them for the host operating system, and then you expose the rest to end user. So that way, any operation on the host, it is not impacting the end VM, right? Or you won't see any performance deviation, or you'll get the exact repeatable performance gains every time. And on this architecture, right? So yeah, we have 176 VM cores, and we have two different variants to support specific kind of workloads. 704 GB or 148 GB, and high storage capacity also. So yeah, this is the HPV4, which was announced as GA a couple of months back, and then quickly moving to the N series, which is which I was referring to earlier. These are the training or inference VM workloads, right? So and this is powered by Intel Sapphire Rapids, and where we have 8 H100s, the H100 GPUs, and 8 CX7s. So the CX7s are acting in the switch mode here, right? So those are connected to the CX7, and then the H100s are connected over NVLink fabric, right? So overall, you have 8 H100 GPUs and 8 400 gigabits per second CX7. And again, like similar to the previous, the HPV4, right? The core reservation. So we have the same thing here. I haven't pictorially shown here, but here, yeah, we take out like 32 cores for the host, and so that yeah, any host activity is not reflected on the VM. And I quickly wanted to go over the different interconnect versions on Azure, right? Yeah, like I was mentioning, the older HB series to all the way to HBV4, so EDR to all the way to NDR. So HBV4, HX1, and the NDV5s, those are the NDR SKUs. And like I mentioned, like since these are exposed over SRIOV, right? So there is no virtualization overhead, right? All the features that are really enabled on the, really available on the host or on-prem side, all of those are available on the VM side also, right? So I'll show some of these impact of these features in one of the upcoming results slide. Quickly, before going there, I just want to call out the HPCAI VM Images, right? So we have curated HPC VM images based on Alma, based on Ubuntu, based on CentOS, etc., with all the required packages already installed, like Mellanox Fed, IP or IB pre-configured, different MPA libraries, including MVAPICH2, the different communication runtimes, the Fabric or UCX, different compute libraries and compilers, and also some vendor-specific tunings, right? For a different, for different SKUs, they may have like different recommendations. So the image or the VM image, when it starts, it identifies, oh, this is my SKU or this is my VM type, and it applies those kind of optimizations. So all these are very transparent to the end user. So yeah, so all the performance results that I'm going to share in the next coming slides, those are, all based on the HPC VM images. So yeah, I'll come to that in a minute. So this is MVAPICH2 on HPV4. Like I mentioned, this is HPV4 is the NDR 400. And here I compare with the previous generation of H series, which is HPV3. HPV3 is HDR and HPV4 is NDR, right? So just comparing two different versions here. And the MVAPICH2 version that I use here is the the MVAPICH2 version, which is the newer one, right? So yeah, so that's the one I use on both platforms. So here we can see slightly better latency for HPV4. And then if you look at the bandwidth, right? I mean, yeah, we have about 2x improvement on bandwidth and bidirectional bandwidth. I mean, and mainly coming from, I mean, HDR to NDR transition, right? 200 to 400 gigabits per second. But I mean, the important point that I want to make here is that, yeah, I mean, the MVAPICH2 is able to like saturate the network without any IDEA overhead, right? So no virtualization overhead, no software overhead, and we are able to hit the peak number. Similar thing here on the ND series. So here, yeah, similar to the previous slide, I compare between NDV4 and NDV5. NDV4 is based on the HDR generation, and NDV5 HDR and A100, and NDV5 is H100 and NDR. Right? So here also, yeah. So yeah, we see slight improvement in latency, especially for large messages. One thing I want to call out is that so there were some build constraints, so we could not get a MVAPICH2 library for this particular flavor that we were using on NDV5. But I assume like, yeah, the performance characteristics are going to be the same. And especially here, right, for both bandwidth and bidirectional bandwidth, like we are able to hit, yeah, close to peak, right, in both the cases. So 200, I mean, 400 and 800, right? So yeah, we are hitting that number. And then quickly on some of the NDR performance distribution, right? So Gilad in today's morning's presentation, like he talked about the congestion control, etc. Right? So this is that in action, like with a on cloud and a full cluster, right? So here, say for example, we take an NDR cluster and let all the pairs communicate at the same time, right? So I mean, n pair or n by 2 pairs communicating at one time, right, at a given time. So yeah, here we can see a single line for bandwidth, and yeah, almost a, I mean, very close, I mean, distribution for the bidirectional bandwidth also, right? So yeah, mainly this, I mean, this is coming from two factors. One is that, yeah, the congestion control is working, doing a good job. And the second one is that there is no oversubscription on the clusters, like all the public Azure clusters are non-oversubscribed. So yeah, so that's another reason we are getting good bandwidth, right? So any customer, I mean, different customers may be running their own workloads, so they won't interact with each other, right, or interfere with each other, right? And quickly jumping to some of the nickel performance on NDV5. So this shows the NVLink Sharp difference. Again, like Gilad was talking about this today morning, right? So here we are taking like 256 GPUs. This one is without NVLink Sharp, right? So basically the idea is to disable NVLink Sharp explicitly or use a driver which doesn't support NVLink Sharp, right? So we can see about 338 or close to 340 gigabytes per second. But when we enable NVLink Sharp, right? So it's closely 480 or 480 gigabytes per second, right? So very close, yeah, very close to the theoretical number. And on the right-hand side, I'll try to go a little bit fast. On the right-hand side, so here again, like 64 node nickel job, but different generation, right? So first we have the NDV4 without Sharp, and then with Sharp, right? So this was about like 189, close to 200 gigabytes per second with the 8 NICs. Again, close to theoretical number, right? With Sharp, it goes to about 227 gigabytes per second. And then again, like this is NDV5 without Sharp, so close to 340. And then with Sharp, it again jumps to the 500, right? This is these both are IB Sharp, and this one is about NVLink Sharp. And quickly going to some of the scaling analysis, right? So in this chart, like I want to show the nickel scaling, right? Specifically, we take three different versions. One is the nickel vanilla, right? I mean, you just take it out of the box and run. This is with some additional platform-specific tuning. Nothing but like, I mean, for a specific scale or message size, you specify a different protocol or algorithm, right? And then finally the Sharp, right? So we can see looking at the scaling efficiency, right? So the tuned version, right, it can get about 90% scaling efficiency, starting from 256 GPUs to all the way to 3K GPUs. And then on the Sharp, yeah, we are close to about 84% efficiency. And then quickly jumping to some of the application results. So this is HPV4 and star CCM. So on the left-hand side, I compare between the different generations, right? So we have HPV2, HPV3, and then HPV4, and again comparing with a very old HC, which is an Intel-based queue also, right? So comparing these different generations, right? So and this is for one particular model, star CCM model, and then for different scales. So yeah, we can see, I mean, as the scale goes up, right? I mean, we are still getting like good performance improvement. This is relative to the HBV2 performance, right? So yeah, we're still getting like good performance improvement even at scale compared to the previous generation. And this is again a slightly different view. I mean, here we are changing the number of total number of VMs here, and then comparing it with the ideal speedup versus the actual speedup, right? So HBV3 is this orange line, and then HBV4 with the Genoa X, you can see even better scaling efficiency. And then quickly jumping to, I mean, yes, similar signature, but two other applications, right? So one is Fluent F1 race car 140 million model, right? And then similar with NAMD with 128 VMs, right? So we are, I mean, here also we can see really good scaling efficiency, right? With Genoa X. So here, I mean, there is one item here, so we identified a BIOS level issue. So that's why I mean, here HPV2 is still showing some better efficiency. But I mean, with the BIOS fix, we were able to. I mean, I have not plotted that here, but with the BIOS fix, we are able to see much better number here. And then on the NAMD model, SMTV 224 million atoms model, right? So this is again comparing two generations, HPV3 and HPV4. Here also same story, like much higher scaling efficiency here, right? And quickly, I mean, jumping back to like the original point that I was trying to make, right? So, I mean, software coming into play and then improving the performance, right? Which is something MVAPICH2 does quite a bit, like, right? I mean, especially when it comes to collectives, etc. So this is at Tutel, one of the recent papers from our group, right? So what we did was we improved the all-to-all algorithm in the MOE model. So instead of like having multiple smaller message IB communication, right, we try to do the intra or over NVLink, like you talk, right, and then you transpose the all-to-all data, and eventually like we can we restrict the communication to just one time and with a larger message, right? So basically queries and then do one communication. So here, yeah, we can see that the improvement in all-to-all itself like was very good, as even as we increase the scale. And this algorithm improvement, along with some of the pipelining optimizations in the framework, we're able to see about like 40% end-to-end performance improvement, right? So yeah, so this again like highlights the point of, I mean, the importance of software-based optimizations, like no matter how hardware is, even though hardware is like moving to next generations quickly, right? So yeah, and which MVAPICH is doing a great job. So with that, let me conclude, and I just want to share some of the pointers, the different HPC GPU VM series, some of the performance blogs, how we can get started on VM deployment, like the VM images that we talked about, like so different aspects. Yep, that's all, and I'm more than happy to take any questions if there are any.
Thank you very much, Jithin, for the great talk. We've got a few minutes left for a few questions from the audience.
Yeah, thank you for the great speech. I have actually two questions. So first, in one of the previous slides, it shows that there's some big difference in the small message latency between the different deployment with different numbers of hops. So is it able for users to customize it on when start the VM?
Oh, so you're talking about this one, right?
Yes.
So
Yeah.
So basically, this is mainly coming from the number of hops, right? So again, this is a factory topology, right? So you'll have neighborhoods, and then you cross the spinals, right? So so that's why this is coming from, like 2 hops versus 4 hops, right? Now how this is exposed to the user, right? So so in Azure, like there are multiple different types of deployments. For example, one customer can get the full cluster, right? So and in those cases, so there is an API that they can use to query the IPNet Discover, and then that they can feed into the Slurm allocator, right? So yeah, now you can allocate nodes based on topology, right? So that's one option. The second option is that, yeah, even on a public cluster deployment, right, where you get X VMs, so right now there is no way they can ask for, oh, I need these 2 VMs which are under the same neighborhood, right? But they can know, oh, this is the distance between these 2 NICs that I have, right? Or they can identify, oh, these many hops I need to take get it to the next NIC. So those are the 2 options. But I also want to make another Uber point here, right? So even though you see this distribution here, right, 1.8 versus say 2.2 or 2.4, right, microsecond differences. If you look at the bandwidth, right, so you don't see that, right? So because you are saturating the network, and then you won't see that, right? So for regular, most of the HPC workloads which are like bandwidth intensive, right? So this won't be an issue for you, right? You don't see those 2 bars on bandwidth distribution.
Yeah, makes sense. And also, HPV4 is showing very good performance comparing to HC VMs. So as I know, in HC VMs, each socket has 1 physical core separated out as a hypervisor CPU core. But for HP series, even HPV4, you have 2 physical cores on each socket as a hypervisor. Is any reason for doing that? Is it because HP series has many more physical core numbers on each socket, or other reasons?
Yeah, so exactly. That was one of the reasons. So HC has actually 2 per socket, right? 2 cores per socket as a reservation. So that's 4 in total, right? And then when it comes to the newer generation, right? So then with the newer generation, the some of the host requirement, right, when it comes to supporting the front-end Ethernet network, right? For example, to support the FPGA cards, etc., right? So, and also to offload some of those functionalities to the host, right? Especially for storage and front-end network, right? So those needed some additional cores. So that's why if you look at all the newer generations, it is a minimum of 8 or 16 cores as reservation. So
Yeah, makes sense.
HC is a very, I mean, one of the first HPC SKU. So that's why we reduced it to like a lower number. And again, also the number of cores available per socket was much lower, right? Yeah.
Yeah, the reason I ask that is actually because as the HP series upgrading, each hypervisor physical cores is actually controlling more and more virtual cores. And
Correct.
is any possibility that in the future that only one hypervisor on each socket in HP series?
So yeah, one of the main reasons we say, for example, in this one, right? So um, uh, here we set we have NPS equal to 2 or NUMA per socket equal to 2. So and we want to keep this balance, right? So it may not be, I mean, like applications it may not be good for applications if you have, say, X cores on this NUMA and Y cores on this NUMA, right? So that's one of the reasons we try to balance it. But yeah, I mean, it doesn't matter from a hypervisor standpoint, or if you have X cores all taken from this NUMA or and none from here, right? So the main motivation was just to balance out the architecture.
Got it. Thanks.
Thank you. Thanks. Yeah, good question. Yeah.
Any more questions? So our next talk was supposed to be a remote one, but the speaker couldn't probably make it. So we're supposed to go for the poster session after this talk, but maybe if you could be patient for a couple of minutes to see if we can get a hold of the speaker. So we'll let you know shortly.